Repel what? They're only going to go in one direction, correct? Okay, but the poles are going to go in the opposite direction, right? And then, we discussed this last time, that there's alternating current in the outlet. And the alternating current means that it's alternating. It's going from plus to minus and plus to minus with a certain frequency, which is in the United States is 60 hertz. So 60 times a second, there's a flip from plus to a minus. And in Europe, it is 50 hertz. 50 times a second. Okay? So if you take what's called an IV curve, IV stands for, does anybody know what IV stands for? Current voltage characteristics. So we're plotting voltage on the horizontal scale and the current on the vertical scale. And then for the forward bias, for the plus, this is the curve. For the reverse, it's locked in. All right, so what happens is it chops the bottom, not the whole bottom, but some of it. And because this pulses come at 60 hertz, this is a conversion from AC to DC voltage. And back in the day, the first product that Motorola made was called Battery Eliminator. First commercial product of the company called Motorola. The reason it's called Motorola is because they made the first radio for the car at a show. Somebody came up with this idea. Family operated business owned by Gauss. What is the application of that? You're charging your cell phone. Your cell phone is charging from DC voltage. The same for your computer. The outlet is AC. So there's circuitry that converts AC to DC. This is the simplest device that can do that. I played with water electrolysis. And water electrolysis is when you can take the current and take the two electrodes, and if you put it in water, you get separation of the charges. So I made this device, and there's a diode in every household, like an old computer power supply, a old VCR or DVD, anything that has a power supply. If you open up, there's going to be a diode, or you can buy it. But for me, it was like easier to scavenge it. And then you connect one of the electrodes through that diode, and that becomes a plus. So it's pumping electrons only in one direction. There's a breakdown voltage, meaning that if you are to increasing the negative voltage, then eventually it's going to break down and it burns. Does that make any sense? So the diode is rated for the voltage, if you look at it, and it's rated for the current. So you need to match for your specific application, making sure that it doesn't get too hot, that it doesn't get reverse blown. Okay, a junction transistor is an interesting device that has three major parts. There's emitter for the electrons, there's a base, and there's a collector. So there's junction, two PN junctions, PN and NP junction. And the cool thing about this device is that you put a forward bias of 0.1, see this is in millivolts, and on the output you get 10 millivolts. You get a factor of 100 increase. It works kind of like an amplifier. And depending on what you apply to the base, you can lock it in. So this signal or this signal, or no signal. And in the digital world, that's what gives you a 1 and a 0. It's the electrical state. And of course, the frequencies nowadays is in gigahertz, so it is cycling, and there are many of these transistors that do this. Metal oxide semiconductor field effect transistor. That's called MOSFET transistor. And we get an N-type silicon that you can buy for relatively cheap. That's a single crystal, and it's doped, and it's an N-type semiconductor. So what is it doped with? More likely, what material? N-type? Okay. And then what we're doing is we are creating the regions that are going to be P-type semiconductors. And that is going to be doped with what? Boron. Okay. And how is it physically done? How would you make a structure like this? There's a photolithographic mask that uses photoresist. So there's a layer of this photoresist that is sensitive to the UV, or now there's UV, but before just regular light. That gets cured. Without getting into too much detail, it's kind of like related to the old type of photography. And then you have a trench. See, there's a trench? And then through that trench, you can deposit boron. So you have boron layer on the surface of silicon. And then it goes through a diffusion process. You put it in a furnace, and boron starts to diffuse to form the P-type areas in the N-type semiconductor. And guess what? The process engineer needs to know and needs to design process. And what are the two parameters of that process? For diffusion that we studied. If you leave it at room temperature, what's going to happen? Nothing. So, to attain diffusion, what would you do with the temperature? You would increase the temperature. Okay? And what is going to happen when you increase the temperature? Boron would start to diffuse. Okay? What's the second parameter? Are you going to leave it there for 1 minute, 1 hour, a whole day? Okay, what is the driving force for diffusion? What's driving diffusion? Why? Why do those species diffuse? Do you remember that picture of the carburization of the gear? A skin layer of carbon that was darker than the rest? Remember we were calculating how thick it is and how long it's going to take? This process is no different. There's exponential dependence on what? Two parameters, temperature and time. And we need to do experiments to figure out how long is it going to take, how thick that boron layer has to be. It's called process development. Guys, it sounds very complicated, but the reality is it's not. I mean, if you're a double E major, then they study this at length, and I'm not a double E major, and you have like 3 majors here, including civil and industrial and mechanical. So all of this is like sounding very complicated, but it's not. because somebody figured this out. You have a cell phone in your pocket, you have a laptop, and there are millions of transistors. And last time I brought, or before I brought this wafer, the processor that you have. Okay. All right, so I wrote this paper. It's called FIB, Failure Analysis of Memory Arrays. And FIB stands for Focused Ion Beam. We have one in the Nano Center. But back in the day, this was published in 2004. We actually did this work maybe in 2002. This was a big deal. It was like a $1 million tool, $1 million machine. And every processor has what's called cache. And cache is short-term memory of the processor where the data is stored. You have RAM, you have memory, other types of memory that's outside of the processor. But the processor has cache. And it needs that cache to perform mathematical operations. Okay. This is the layout of the cell that has 6 transistors. Okay, and this was the state-of-the-art thing back in 2002, like a while ago. And the electrical engineers would test the processor. They tried to address each individual cell and see if that cell retains ones or zeros. It takes 6 transistors for the logic to give you this fast operation. It's the memory, cache memory is inside the processor. That's what makes it fast. Because otherwise it just takes too long to get the signal out of the processor, through the bus, to the memory, all that good stuff. Okay? And then, once in a while, you're going to see defects like this. And these defects, that's what kills your processor. This is 3 microns, relatively big. And Larry Rice is the best microscopist I've ever known. He only had a AA degree. So he went to a trade school, and his hands were made out of gold. And I was a PhD engineer, and I learned from Larry how to do the etching. So this is cache, right here. A certain layer of the processor. I mean, it didn't change that much, but that's what it looks like. There's some contacts. And then the EE guy is giving you the physical address where the individual cell is failing, where it failed. There's a physical address. Then, there was pre-EI era. You had to somehow convert that into the physical location. It's like, okay, you're going to show up for Volinsky's lecture, and VEH, what's the room number? 101? Whatever the room, I don't even remember, but you physically remember where you're going, right? Or what if you were in a foreign country? Like on Thursday, the lecture is going to be in Montreal, Canada. How are you going to make it there? You know what I mean? How do you get there when you travel? Can you imagine with GPS not being there? I remember. You know how we used to drive? Maps. So you go to Walmart, and for $10, you buy an album of the maps of the United States. So as a grad student, I drove from Minneapolis to San Francisco. You know, and you get a sense of direction. Otherwise, there is no GPS. The reason I'm asking you or telling you this is because you have to count, and then you would put marks. And you count 1, 2, 3, 4, 5. And if you make a mistake, you're not going to find this particular bit. Now, this is the transistor. So this is the gate, and this is the width of the gate. You can see this is about 90 nanometers. And the semiconductor nodes are measured in this distance. So what I did is, because I don't know what the current node is, I just went in here, and you see here, the minimum gate length of modern semiconductor transistors is around 18 nanometers for commercial 5 nanometer nodes. So 18 nanometers. Contact gate pitch of 51 nanometers and metal pitch of 30 nanometers. So whenever they tell you there's a 5 nanometer node, it ain't 5 nanometers. It's a marketing gimmick. What did it say? 30 nanometers. So this distance here is 90 nanometers. In 20 plus years, it was reduced by a factor of 3. But what does this mean? It means that you can put on the same real estate, you put more transistors. Like downtown St. Pete used to have houses. They demolished those houses and put condominiums. And for the same amount of land, you grow things up and you increase population density. Back in the day, now what kind of speed do you get on your cell phone when you connect to the cell phone tower, the data? Oh, they've changed things around. This is the University of South Florida. You get a gigabit, roughly. And if you do this on your cell phone, you're probably going to get 1/10 of that, and that is pretty good. See, it's both ways. Actually, upload is a bit higher than the download. How much bandwidth do you need to watch a movie? See, everybody's worried about this download speed. It depends on what you do. If you're watching content, so from the Netflix server, wherever you're watching it, comes to you, right? These are blazing speeds. I don't think you can get this kind of speed from Spectrum or maybe Verizon with the Fios or whatever the speed is. So, my job was to find those defects and classify them. These are the vias that actually connect to the transistors that's made out of tungsten, and then eventually it goes to the metallization layers, which nowadays, I don't know, like more than 10 for sure. You see, this is a transistor, and this via is supposed to come down and make electrical contact. You see there's a contact missing because they didn't dig the trench deep enough. And you have to be very tedious, but tedious like almost like a jewelry maker. To be a microscopist, a good one. It's not like being very accurate like a CPA. See, this is where I personally fail. I fail in the details. I cannot do the numbers very accurately, but something with my hands like this, because you have to slice it and move slowly into the defect and say, okay, incomplete contact, or there's missing pattern. But this is the flow. You find the location, and that is, a lecture in Toronto on Thursday, or Montreal. I'll give you the address. Are you going to make it there? take a plane and then rent a car or take a bike. You see what I mean? Like this is a pain in the ass process. If you miss by one, you're going to end up in Honolulu. Okay. You deprocess it down to the desired layer, and as you're polishing down the chip, it looks different. So Larry took the chip and was polishing it by hand. And when you do this by hand, you realize that you're not evenly polishing it. So you constantly polish it, look in the microscope, polish it, look in the microscope. You use a laser or a scribe to mark the location. Then you place it into the Focustan V machine, and you start to cut in slice by slice by slice by slice. Imagine a stick of butter, and somebody hid something inside that butter. Somebody put a quarter in there. You don't see it. It's inside the butter stick. So you take a knife and you slice it and you slice it and you slice it and you slice it, eventually when you get to that quarter. This is a pain in the ass. Verify counting, no defect. No defect means that you wasted 2 hours of your time. I want to find the defect. And then you take the pictures and you send it to the process engineer. And they would figure out how to change the process to control the structure, to control the process, to control the structure, to control the property. Look at this. Another example. This contact doesn't go all the way down. These are my marks. Missing pattern. You see here? And missing pattern could be due to a defect that you go into the bunny suit. Have you seen the Intel commercials? Da da da, da da da, and the guy in the bunny suit? Have you ever seen a person in a bunny suit? No? Yeah. This is it. So if you ever end up working for a semiconductor manufacturer, you're going to be working in the clean room. And the clean room is good, but the managers schedule like maybe 5 meetings during the day. So for you to go in and put on the latex gloves and gown like this is nothing. Like you're talking about like the full-blown mask and the glasses and everything, and you sweat like a pig. It's cold in there, but still, it's a job for young people. How about this? Look at this. This steel bar is 200 nanometers. There's a faint layer, and this is 20 nanometers. 20 nanometers is how many angstroms? How many angstroms in a nanometer? I told you many times, please write it down. 10 angstroms in 1 nanometer. How big is an atom? How big is an atom? Guys, I'm making this class. I'm trying to make it very complete. There's a lot of material, but what I'm trying to convey to you are things that are actually important. Because I announced that the next lecture on Thursday is going to be in Montreal. How the heck are you going to get there? You know what I mean? I say how many angstroms are in a nanometer. That's what really matters. That's what we need to know. Right? Look, there's a very faint layer. This little dots, these are atoms. vias are shorter. And there's some advanced techniques, titanium, where you see the brighter images that is titanium. Now look at the resolution. See, a company can afford a tool that is $500,000. Why? Because each processor is $500. And if you can improve the yield by 1%, it's a huge profit for the company. Anyway, I had fun. And I hope that you are also going to have fun at your job. Most people work for money. At some point, you're going to be working for fun. I mean, don't get me wrong, you still get paid. But if you have fun, your job is really a job. And if you don't have a job, you have to that's what you're doing. Are you having fun studying? Why not? Is it stressful? Why? Because you're afraid to fail? And what's going to happen if you fail?
You gotta do it again and lose more money.
Do it again? I heard McDonald's is hiring. Somebody has to do it. Somebody has to be a plumber, somebody has to be an electrician. Personally, for me, I was like an overachiever. Getting at these like a failure. Look back, all that stress. I wish I saved my nerve cells. Okay. Ferroelectric ceramics. So we're going to switch gears a little bit. Do you have any questions about semiconductors? What you need to know is that there are intrinsic, extrinsic semiconductors, P-type and N-type, and a diode only passes one direction. Transistor amplifies it, that's not to get a 1 and a 0, and you can make a digital bicycle. Pretty straightforward. See, the way I was teaching this course, I was trying to build layers upon layers. I told you that we talked about X-ray diffraction. What's the wavelength of copper alpha radiation? When was the last time you visited a dentist? Huh? A week ago. Did it take x-rays? Okay, well, you all have taken x-rays, right? Okay, where do those x-rays come from? You know they import them from Canada, those x-rays. They travel on a plane. What's the wavelength of visible light? We discussed all this. I showed you the roughly. Have you ever had a laser pointer? Okay. Have you played with your cat and the laser pointer? The cat went crazy. You remember? Have you ever looked at that laser pointer that was a red laser, probably? Did it say wavelength and said what it was? You remember it on your laser pointer? It's a good guess. Can somebody check to see what the wavelength of a red laser? We'll talk about lasers too. They're coming. 630 to 700 nanometers. So ballpark is 1 micron, which means that an optical microscope, the resolution is going to be roughly 1 micron. But if you look at the electron microscope, that has much higher resolution because of the wavelength. So X-rays for copper K alpha radiation is 1.54 angstrom. That's the wavelength of X-ray from copper. That means that we can use that to study matter. because the sizes of the atoms are in the angstroms range. The size of an atom is like an angstrom, about, plus or minus, whatever. So this was a good guess. You made a good educated guess. So what I don't care that he didn't say 640, because I don't remember that myself, but you were in the ballpark, 400 nanometers. And 400 nanometers is how many angstroms? There are 10 angstroms in an atom? (400 times 10 is what? There you go. And it is very important, extremely important, by the way, whenever you show something. How many of you bought stuff on the internet and it came, I was like this big? You know what I'm talking about? What did you buy? It's tiny. Okay. How about the other way? Something was too big. Okay, but when you look on the internet, it looked okay, right? Guys, pay attention to this. What is this called here? A micron bar or a scale bar. Whenever you show anything like this, you need to show the scale. And most of the microscopes do that automatic. Optical microscope, you need an optical ruler to do that. Just a side note. All right. Ferroelectric ceramics experience what's called spontaneous polarization. And we're going to talk about Curie temperature in the next set of slides, but the idea is that there's a titanium atom right in the middle, and you can see how much it shifted, 0.006 nanometers. And how many angstroms is that? Literally, there's one atom, and there's a titanium atom, and it's 0.06 angstroms. So this shift is less than the atomic dimension. When was the last time you did a barbecue? Are you familiar with the Weber barbecue? Weber? The grill? How does it work? It's connected to the gas tank, right? Okay. So propane. What do? You open the propane tank, and then what? Activate the spark plug. How do you activate it exactly, if you remember? It starts clicking. It does not start clicking. You push it with your finger, like this. When was the last time you changed batteries in that thing? Never. Why? There are no batteries. Okay, so piezoelectric materials generate electricity. They generate potential voltage when you deform them. So this is in the stress-free state. That's when you're pushing on this red button of the Weber, and then it sparks. It generates a spark, and that spark is enough to ignite propane. The same thing is in the piezo lighter. Are you familiar with the piezo lighter, the one that you just push down? Have you ever taken that lighter apart? Or have you seen what's inside? If you do, be very careful, because if you are pressing on that, that generates about 10,000 volts. You don't get killed, but you get electrocuted. So the idea here is that we take this material, we deform it. And as a result of this deformation, there's voltage that's being generated. Okay, we talked about electrical conductivity, electrical resistivity. These are materials properties. We tried to make them geometry independent. We talked about three types in terms of the electrical properties as conductors, semiconductors, and insulators. Looked at the effects of temperature, defects, and plastic deformation and resistivity. And then looked at the pure semiconductors. Talked about doping with boron or with phosphorus to make it a p-type versus n-type semiconductor. And just touched on other electrical effects such as ferroelectricity and piezoelectricity. Any questions about electrical properties? It's to control the process, to control the structure, to control the properties. Chapter, 19 is thermal properties. So we're going to talk about heat and talk about heat capacity and thermal expansion and thermal conductivity and thermal shock resistance. And also discuss it from the standpoint of three classes of materials, which are what? Metals, ceramics, and polymers. Three major classes of materials. Okay, and you're gonna talk about it in other classes, but the first property of a material is called heat capacity. It's the property that allows material to absorb heat. And quantitatively, it's the energy that's required to produce a rise in temperature for 1 mole of material. It's measured, it's noted by the letter C. Heat capacity is measured in joules per mole per Kelvin, and it's equal to dQ over dt, where the energy input is in joules per mole and the temperature change is in Kelvin, absolute temperature. There are two ways to measure heat capacity, and that's where you get C sub P and C sub V. Heat capacity sub P is for the constant pressure, and C sub V is for the constant volume. And typically the constant pressure is higher than the volume. And the units are joules per mole per Kelvin. In the English, it's BTUs per pound mole per Fahrenheit. And you can only imagine this conversion factors that's going to be like where else do you get the BTUs? Air conditioners, okay. And these are English units. How do you size an air conditioner? Volume and also heat load. Like this room has no windows. So the heat load is probably, but that door is not insulated. And how is the sizing of the air conditioning measured in the United States? Have you heard about a ton? What's a ton? No, it's 12,000 BTUs. 1 ton is at 12,000 BTUs. So 1.5 tons is 18,000 BTUs. 2 tons is 24,000 BTUs. But if you go to Europe, they're going to give you the same thing, but in joules. And because I live in the United States, I know what a 2-ton AC is and what's a 1 ton. And, okay. Let's take a look how heat capacity depends on the temperature. This is C sub V. as a function of temperature. It goes up, and then eventually it reaches saturation value at higher temperature, where it is constant. It is equal to 3 times the gas constant. The gas constant is 8.31 joules per mole per Kelvin. And each material has what's called Debye temperature, which is where that saturation starts. Okay. You're boiling hot tea, and then you got a spoon. You put that spoon in the boiling water. What's happening? The spoon is heated up. What is happening to the material when the spoon is heated up? The atoms are vibrating. So, the vibrating system, any kind of vibrating system, has 2 parameters associated with the vibration. What are those parameters? Amplitude and frequency. Okay. The frequency of vibrating atoms doesn't change that much. What's the natural vibrating frequency of most of the atoms? The book doesn't tell you, but I will. It's 10 to the 13 hertz. 10 to the 13 hertz is the vibrating frequency. So what's happening as the temperature is raised, the amplitude is increased. This is the reason why materials expand when they're heated up, most of them. But let's get there when we get there. So, what you need to remember is that the heat capacity for the volume at saturation is equal to 3 times R. And typically this Debye temperature of the transition is less than the room temperature. So this energy is stored as the vibration of the individual atoms. As we're increasing the temperature, the average energy of the atomic vibration increases. You can see it's very nonlinear. Normal position of the atoms, and the blue ones is when they're vibrating. They're called lattice waves, or the other term is phonons. Phonons are lattice vibrations. And as part of my graduate work, I had to take solid state physics of the physics department. Do you want my honest advice for your studies for the rest of your career? Do you want it? Yes. Okay. Have you ever flunked a class or were close to it? Yes? No? Maybe? I don't want you to fail. Okay? I can tell you personally that if you take a course outside of your major, that's when you become senior, you take a course from a different department, you're more likely to fail it. For me, solid state physics was hard because I could not make a physical connection. What the heck is a phonon? And to write an equation for the atomic vibration of each individual atom. But phonons are atomic vibrations. So the physicists, first of all, they want to look at everything at 0 Kelvin, or maybe 4 Kelvin, which is the minimum temperature that can be experimentally attained. And I want the device to work at room temperature, unless there's a specific application where you go into space and Mars and Moon and whatnot. Okay, this is the comparison of the heat, specific heat for polymers, ceramics, and metals. And you can see that for polymers it is kind of like higher, but it doesn't vary that much, maybe by a factor of 2 here, but here for the metals by a factor of 10. So the heat capacity has to do with the ability to store heat. Like you heat something up and then it's going to cool down. The gold is going to do that faster. Aluminum, less fast. Plastics, less fast. And what happens during the heating is all of the materials expand. There are some exceptions, like ice. Water expands when it's frozen, but we're not going to discuss that part. So initially we had the length of your material L, and then we heated it up, and it elongated. From the mechanics perspective, it doesn't matter why this thing elongated. It means that we attain strain. So look at this rubber band. See, I'm stretching it, and I can calculate strain as the elongation divided by the original, minus the original length divided by the original length. If I heat it up and it expands, from the material perspective, it's the same as if I'd done that. So that's called thermal strain.
See?
Final strain minus the initial strain divided by the initial, which is equal to linear coefficient of thermal expansion times delta T. T final minus T initial. And if we look at the potential energy versus the interatomic distance, most of the materials would give you asymmetric curve. So here is your R0 at lower temperature, then you keep increasing the temperature, and this is your amplitude of the atomic vibration that increases. And as a result, we're moving over here. So this is an example of the asymmetric curve. This is an example of symmetric curve. If the curve is symmetric, there's no thermal expansion. It just vibrates around the center position. Does that make any sense? So for most of the materials, the potential energy well, which you've done the homework on in the beginning of the class, it's actually asymmetric, and the equilibrium distance is increasing from R0 to R2, 3, 4, 5, and so on and so forth. Here, the position does not change. R1, R2, R3 is the same. That's because the curve is symmetric. And most of the materials are like this. They're asymmetric. Coefficient of thermal expansion does not have the units. Or does it? Let's look at the formula. What are the units of length? What do you measure length in? Meters. Okay? So if you take meters and you subtract meters, what do you get? Meters. And then if you take meters and you divide it by meters, what do you get? No units. Okay. This is the thermal expansion coefficient. What's the temperature measured in? Degrees. Okay, so we have something multiplied by degrees, and degrees need to cancel out. What needs to be the unit for the thermal expansion coefficient? 1 over degree. 1 over degrees times degrees cancels out. You see? Does everybody see that? Okay, so the thermal expansion coefficient, alpha, is expressed as 10 to the negative 6 per degree. And 10 to the negative 6 is, what do we call it? Pico, nano, kilo, meta, mega. 10 to the negative 6. Okay, guys, I'm here. Let's do this once and for all. And nano, and write it down. Nano is 10 to negative 9. Please write it down. And a micro is 10 to the negative 6. And a milli, vanilli, is 10 to the negative 3. And centi, okay, and kilo, 10 to the 3, and mega, and giga. Okay, did you write it all down? So if I ask you again, you can look at it again. I see you're not writing. You remember that by heart? Who remembers it and didn't need me to remind? Okay, good. Be like him. Because at some point, you're not going to be able to get that piece of paper that said, this is something that you're expected to know. I'm sorry. If you're in engineering field, I don't care if it's industrial, civil, electrical, you need to know the megas and the gigas and the nanos and the angstroms. Okay, so this is not 145 to 180. It's 145 times 10 to the negative 6. Does everybody understand how this works? It's whatever this number times 10 to the negative 6. And you see here that the thermal expansion of polymers is the highest because the bonds are weaker and they're secondary. And then they will have aluminum and ceramics that are comparable. Thermal expansion coefficient at room temperature. Okay, let's do an example. A copper wire, 15 meters long, is cooled from 40 to minus 9 degrees. How much change in length will happen? And the thermal expansion coefficient of copper is actually quite high. 16.5, 10 to the negative 6 per degree. So we can take the equation for the thermal expansion, and we can write that delta L is equal to the alpha, the thermal expansion coefficient, times L0. L0 is the original length, times delta T. Delta T from 40 to minus 9 is actually 49 degrees, because it's 40 minus 9. And then we get 16.5 10 to the negative 6 per degree times 15 meters. That's an SI units is the unit. Times 49 degrees. That's going to give us 0.012 meters, which is equal to 12 millimeters. And 12 millimeters is how many inches? Show me an inch. Show me an inch. Okay. So how many centimeters in an inch? Like how much? Like that's a little bit too high. 2.54 to be exact. 3 is fine. Around 3. It depends on what you do. If you're in civil engineering and you're off by half an inch, drywall ain't gonna fit. What's the thickness of the drywall? 3/8 or sometimes half for a good one, or maybe a quarter. You civil? Okay, well, you've done some construction. Okay, it matters, the size matters. 12 millimeters, you can see with your naked eye. This is 12 millimeters right here. This is the width of my pinky, is 12 millimeters. You will see it with your naked eye. Okay, thermal conductivity. What is the physical meaning of thermal conductivity? We just talked about electrical conductivity. What is thermal conductivity? Okay, I have this, and I'm holding it in my hand, and I take a lighter, and I heat this end up. Now what's going to happen? In this case, rubber is going to start to burn, but nothing's going to happen, well, unless I do it like this. You see what I mean? They say they were born with a silver spoon in their mouth. That's not a good thing. Why? Why silver spoon is no good? Because the baby's going to get burned. Okay? 40-year law states that the heat flux, Q, which is joules per meter squared per second, is equal to minus K dt dx. dt dx is a temperature gradient. K is the thermal conductivity. So one condition for this thing to happen is that there has to be temperature differential. And temperature is going to travel from the hot side to the cold side. How does it work? It's the wave of those atomic vibrations that start here and eventually propagate over there. But it takes some time. By the way, conductivity is measured in watts per meter per Kelvin. And here's a comparison. Metals are the highest because they have those free electrons. If you ever go to Germany, if you ever go to Dresden, in Dresden they have hygiene museum. Can you imagine? That's what it's called, hygiene museum. And they have a lot of interesting things about like human body and all that. And there's this device, and it says, touch me. And what it is a cylinder, and there are two pipes, and they're all painted the same color, dark color. And those pipes are going around like this in a spiral. Okay? And I take my hand without reading the instructions. It says touch me. I touch, and I take my hand off because I think that I'm burning. And there are two pipes going in the spiral. One has warm water, and the other one has cold water. And then I had to force myself to actually touch it and leave my hand on. And you cannot imagine the emotional or whatever roller coaster that my brain went through, because I couldn't figure out if it was hot or if it was cold. And you know, the effect only lasts one time. I mean, I wouldn't compare it to like drugs, but it was pretty close to being on some sort of drugs. Because you have your hand and you're touching something. It's about this size, so you put your hand, you have good contact. So the way our skin works, it does not know the absolute temperature, but it knows the temperature difference between the 2 points close to the skin. And that's exactly what they had. So, you know, I touch my hand now, and I feel that my hand is warm. I feel it with this hand. And also I get the heat from this hand going here, so I start to feel the heat. A very interesting experience. So if you ever see this kind of device, I suggest that you try it, because it's interesting sensory experience. Okay, the highest conductors of heat are metals, followed by ceramics, followed by polymers. because, again, this is a propagation of the atomic vibration wave that propagates from here to here. And some materials are very good insulators and some are not. We'll get back to this. But so far we discussed thermal conductivity and the heat capacity. These are two different things. For civil engineering, what you want is you want the wall to be heated during the day and emit that heat at night. For the air conditioning, you want to have good insulation. Do you run your AC in your car when you're not in the car? Well, you should, but you never leave children and animals in your car. It's very dangerous. But when you get into the car, you start the air conditioning. And when you leave the car, you turn off the car, the air conditioning stops. Does that make any sense? But for your house, the best thing is to run your air conditioning continuously and make sure that you have very good insulation. Okay. Thermal stress. We already established and discussed that materials expand and contract, but the temperature gradient leads to different changes in that expansion and contraction. So stress, sigma, is equal to E, elastic modulus, times the strain, which is alpha times delta T. So E alpha delta T. Did I show you the paper from Corrosion Society about the ranking of the coatings for offshore drilling protection? Yes? Mechanical aspects of anti-corrosive coatings performance tests. Coating fails. Can fail like this, can be failing with delamination. Thermal stress is equal to modulus times the difference between the thermal expansion coefficient and delta T. Is this the same formula as this? E times alpha delta T. Pretty much, right? Okay. A brass is stress-free at room temperature, 20 degrees C. If it's heated up, but prevented from lengthening, what's the temperature has to be that the stress would reach 172 megapascals? In mechanics, this is called statically indeterminate problem. Remember? Civil you have to take mechanics to solids, but industrials you don't have to take. Okay. So imagine this. There are two walls like this, and in between them there's a piece of metal, and you're heating it up, so it wants to expand, but you're preventing its expansion by very narrow and rigid walls. What's going to happen? What happens to the material that wants to expand but it's not allowed to? There's going to be stress. Mechanical stress that's arising. So first we assume that the material is unconstrained and we'll let it expand. Then what we're gonna do is we're gonna push it back. This is actually how the problems are solved in mechanics. And follow this calculation. And it seems like I'm out of time, so we're gonna pick it up on Thursday. But do you have any questions? Yes?
Since we're examining answers, can you tell us like the chapters to begin
I will on Tuesday, at least. No, today's Tuesday, next Tuesday. The next exam is on Thursday. So,
Can you try and do it for Thursday so you have extra time to study?
Yes.
Because other classes are doing the same thing, trying to get their last exam in before test 3 week. So if we had a little more time to study that.
all right, the format is going to be the same. 5 problems, 4 problems worth 100 points, and a bonus worth of 10 points. Yes?
Are you gonna give us the layout of each question?
I have the mechanics test with me, right here. So I can do it for mechanics. I don't have it for this class yet because it hasn't been made yet. What are you guys doing in the help session? Composites? You covered chapter 18, so electrical properties? Okay, I don't think we're gonna go past the 18. Yes, sir.
So what do you know what chapter we should be mostly focused on then?
Yeah, 0. I don't have an answer for you right now, but I will on Thursday. I heard you. You want extra time to study? I'm working on it.
Thank you.
Then on Friday, you think it's possible for them to kind of help us through that process?
Yes. So come on Thursday, on Friday. By the way, last Friday there was like 5 people in there, and I'm really happy and I'm pleased to see you because I see a majority. I don't know what happened, but I like this.
Next question.
Maybe you can fit it on last Friday to be extra credit. Me, that might
Extra
help.
credit.
That might help.
You know how you're gonna get extra credit? I tell you how. No. This teaching evaluations. I historically for like 20 years get very low response rate, like less than 10%. Okay. So I talk to other faculty. You know what they do? They say if the response rate is going to be 70% and higher at a certain time, then everybody gets extra percent or whatever. And I don't mind doing that. So, I don't care what you write. You can say I'm an asshole. You can say I'm the best thing on this planet. I don't care, but I'm looking for a high response rate. Is that cool?
Yes.
Okay. So, I mean, all of the other stuff, AI and the paper and all that good stuff is fine. I just need a very high response rate, over 70%, and you're going to get an extra percent for your grade. But it has to be a team effort. So if you're slacking and you're not writing about me, then the rest are not going to get a percent. Yeah?
Could you send like a campus announcement?
Absolutely. I don't know when those teaching evaluations come in.
Yeah.
I mean, I try to get the response for AI and this and that, and at the end of the day,
It might be after the final exam, so.
I don't think so. No.
It's usually during test 3 week. Yeah, so it is after the
It is during the test-free week. By the way, during the test-free week, we're going to have 2 more lectures here. And that would be the ultimate test, because, you know, if my concerts are sold out and I'm Diana Ross, I'm going to see. After the exam, can you imagine? What do I need to promise? I tell you what, I have a feeling that students will come after the exam for those 2 lectures on the 28th and the 30th of April. I'm not going to tell you the reason, but I think what? What's a guess? Yes?
What about Friday? Are there any more help session on Friday next week?
Yes, there's a help session this Friday.
But next week, no?
Do you want a help session next Friday? That will be after the exam, like the day after the exam. I tell you what the value would be. If we go over the solutions for the test the next day, see, I was a student, and you know what my problem was always? Has been a problem? Okay, Alex, here's your homework. What do I do? I look at the grade. Okay, and I file it. I wish, and I suggest what you do is if your grade is not 100%, you figure out why. You close the loop. You see my point? And that's the value for the educational process. So, I'm going to tell you what's on the exam. I'm going to take this piece of paper out. I'm going to say the first problem is about composite materials, and you're supposed to calculate the elastic modulus of this fiber composite. And you know what you're going to do? You're going to listen to me. And then you're going to go to the book and solve this similar type of problem. And then you're going to go to the help session on Friday, and instead of 5 people, there's going to be 55 at least people. I would be happy with 85, 100% attendance. And, it's called behavior modification. If I give you a coupon for $5 off Starbucks, what's going to happen? $5 off a cup of coffee. Which means that if you buy the cheapest one, it's going to be free. You know what's going to happen? You know what's going to happen? How many of you would go get coffee at the library? Do they still have Starbucks there?
Yep.
$5 off. Raise your hand if you'll go, even if you don't drink coffee. No? No? Okay. Sorry, I tried my best.
Try Chick-fil-A.
Chick-fil-A. Okay, $10 off Chick-fil-A.